Okay, I was told to introduce myself, so I'll do that. I'm Johan. I work at Nighting doing open source work, and I'm going to present to you something I've been working on, and I'm going to explain what it is. So we call it optimistic execution of RISC-V and verified in Tapscript. And this is obviously part of the covenant discussion, since this all gets possible as an effect of having covenants available in Bitcoin script. Okay, so what is this optimistic execution of RISC-V in Tapscript? It's a proof of concept we built. It's working. We have code running right now, so you can play around with it. Optimistic execution means, I'm going to go into it, but this is kind of built on the Merklei's all the things proposal by Salvatore, and it's about getting better and more expressive smart contracts into Bitcoin without increasing the on-chain footprint. So this is what I'm going to go through. I'm going to just tell you a bit about the terms I'm using in this talk. I'm going to tell you about what features and what we get from having this available on Bitcoin. I'm going to do a technical deep dive where I'm going to go from end to end, where you start with like a high-level language and down to the Bitcoin script at the end. Then I'm going to do a demo and take a brief look into the future. So what is optimistic execution? Optimistic execution means that we want to perform as much as possible of the computation off-chain and only perform it on-chain if we have to. And if the incentives are aligned, then we expect the on-chain footprint to never actually get into the worst case, because it will be expensive for those trying to cheat in this game. So in the best case, we are only putting the input to the program we're running on chain, since that is data that has to be available for everybody verifying the program. So that has to go on chain. And I'm saying that in the worst case, you only need a smallish proof to go on chain, and that's it. I'm saying it's smallish because it's very, very small compared to the actual computation, but it's larger than the best case. RISC-V, what is that? It's a reduced instruction set architecture, and the nice thing about it is that it's fairly simple. So since we're emulating all of this in Bitcoin script, we need to be able to actually express what the RISC-V architecture is doing in Bitcoin script. It's also getting a lot of traction, so it has a lot of compilers, tooling, things you can use when you are building programs using RISC-V. However, we can basically use any like high-level language that has a RISC-V compiler when writing these Bitcoin contracts. The limitations, however, are that it has to be deterministic, since everybody needs to be able to verify the computation and get to the same result. We need to make sure that computation is always deterministic. That means like things like no concurrency, no operating system calls, nothing like that. But usually that's fine. You can use a language like Rust or C or a lot of other languages. So what's Merklei's all the things, or MAT in short? It was a proposal by Salvatore made in 2022, I think. It's a fraud-proof framework, meaning that it's, as I mentioned, it's optimistic. You only like put this real proofs on chain if you catch someone cheating. It's called Merklei's all the things because we Merkleize the script, the program itself. We have like this compiled program. We Merkleize it in effect of having it being Merkleized in the taproot tree. We also take the memory of the computer we're emulating. We're Merkleizing the full memory and only committing the state root to an actual Bitcoin transaction. And this is very powerful, but it gives you a lot of memory to play with. You can have gigabytes of memory, and you only put this hash, the state root of the memory, on-chain. Finally, we Merkleize the computational trace. So in case somebody's cheating, we ask them to prove or to show us the computation it did. So we go through the computation, Merkleize the states, all the states in the computation, and we Merkleize that again, and put the state or the computational trace root on-chain. To enable math, it has an accompanying opcode that was also mentioned during the panel called check contract verify. It's very simple, which is also why I like it. You just check that the input key has some internal key and is tweaked with some data, and also that it's tweaked with some taproot. And you can do the same with the output key. And that way you can take the state from the input, modify it somehow, and then commit it to in the output. In addition, we use cat a lot because we're working with Merkle trees. So cat is very, very useful in that regards. So what does this give us? Well, it lets us write, developers write Bitcoin contracts in higher level languages. Bitcoin script is much like assembly, and if the vast majority of software developers these days, they don't ever have to deal with assembly code. So why do Bitcoin developers still need to deal with assembly code? So if you have this full suite of tools where we can write high-level languages and compile it down to Bitcoin script, I think that would be very helpful in getting more developers working on Bitcoin scripting. Since it's optimistic, all the execution is happening off-chain. That means you get a very, very small on-chain footprint, which is nice from a chain and fee perspective. I listed some use cases here. There are probably many more. One of the most sought after that I know is like shared UTXO schemes, where you can have like contracts, payment pools, vault type constructions, where many users are sharing a UTXO on-chain, and they have like their off-chain rules about who is owed what from the UTXO. So you can build that. You can also use it as a building blocks to build bridges for sidechains and rollups. And you can also optimistically create CK verifiers using this framework, which is again a building block that you can use for a lot of other interesting stuff. Okay, so let's do a technical deep dive. I'm gonna start from see this from like a developer's perspective. If he wants to write some contract using this framework, I'm gonna go step by step. How do we go from the high-level language to what we put on chain? So we start out with a high-level language which has compiler support for RISC-V. Here's an example of a Rust program that you can do. This one will just read some integer from standard input. This is what's going to be put on chain when you are kind of like emulating that you're running this thing on chain. You're going to do some computation using this, and then you're going to write the output to standard output again. So it's much like writing a regular command line tool, really. And that was also what we tried to achieve with this. So the result you're writing here, it can be simple. It can be like a true-false statement telling you whether you're able to claim the money. Or if we have like amount introspection, you can say that this is the value you're able to like take out of the contract, for example. When that is done, we build it, and we target like a 32-bit RISC-V bare metal target that doesn't have a lot of features, but it doesn't have a standard library. It doesn't have like operating system underneath it, but it has what we need. And that gives you a binary. And this is a RISC-V binary that you can disassemble and look at the opcodes or whatever the CPU would run when it runs this binary. And this is what we use to convert or to actually create the Bitcoin scripts. So we're going to just have a program, go through every opcode in the RISC-V binary, look at it, and then create an accompanying Bitcoin script that does the same as this one opcode is doing on the CPU. And in effect, like every script we're creating is basically doing the same thing. Luckily, RISC-V is fairly simple. So as an example here, we're looking at the add operation. It takes whatever is in a register, adds, in this case, 256 to it, and then stores it back into another, or in this case, the same register, but it could be any register. So this is basically what every opcode does. It takes some value in a register, does something with it, write it back into another register. So in this case, was that a block? Oh, let's do this. Yeah, so basically we have this memory root, which we fetch from the input of the transaction. In this case, I've highlighted like the program counter register and the A0 register. The script is going to validate first. So the runner of this, or the creator of this transaction has to provide a witness, telling you something about the memory. So it's going to put like the value found in A0. It's going to put also add a Merkle proof to this value. And the first thing the script is going to do is check that this value is correct. It's going to take the input memory, or the state root to the input memory. It's going to check that this Merkle proof is valid for this value of A0. Then it's going to add 256 to it. We also increment the program counter. That's something we do for every script. And then we're going to take these two new values together with the Merkle proofs we have already. We're building a new Merkle root, and then we take that Merkle root and check that that's the same one as is committed to in the output. And this is how we validate every state transition of the VM. When that is done, we're going to take all the scripts for all those lines in the assembly file, and then we're going to add them as scripts in a tap tree. Then we're going to assemble the tap tree, and that's what goes on-chain. Now, when this contract output is on-chain, anybody can claim it or try to claim it. So in this case, let's say Bob tries to spend this output. In order to do that, he has to like provide some input and output to the program. So he says like, this is my input. When I run this, I'll get this output. Somebody challenge me if I'm wrong. In order to disincentivize actually trying this with invalid data, we also make him like add a collateral input to this transaction. And there's a time lock on the output, giving anybody time to verify this data and try to challenge him if there's something wrong. And that's the nice thing here, right? Since the input is valid or is in plain text in the input, in the witness, anybody that knows what this program is doing under the hood can try to run it with this input and check whether the output is correct. So let's say Alice looks at this and figures out, oh, Bob is actually not entitled to this money. He ran it with some input, but the output is wrong. He claimed it was something else. Then Alice will challenge Bob. And she does that by spending his output before the time lock expires. Again, we want her to have some skin in the game, so she'll add some collateral as well in order to not challenge something that's actually correct. And when Alice challenges Bob, that means Bob has to show Alice how he got to this result. So again, we'll post a Merkle root in the witness for Bob, and the Merkle root is a Merkle root to the computational trace that Bob performed. So this is something you may be familiar with, but you have this trace, and for every state, you can you like say, this is my starting state and this is my ending state when performing some kind of operation, and then you build a Merkle tree such that you can bisect down to this state. And this is the next part of the protocol, the trace bisection protocol. Since Alice knew the initial state of the memory, and she has the input, she can run the whole thing and figure out that, at some point, the trace I get and the one that Bob put on chain, they diverge. So at some point, there has to be Bob was doing something wrong. So she'll play this challenge response game where she asks him to reveal subtrees in the trace, and finally, you get down to the state where they disagree. And when you get to this state I, where they did agree, and in state I+1, in this case, they don't agree. And here is where this script we just created in the beginning comes in. So Bob is required to run this script, and if he's able to provide a witness to the script such that he can take the state from state I to state I+1, then he actually performed the computation correctly. And he can burn Alice collateral, since she tried to challenge him even though he did it correctly. And if he can't do it, then after a time lock, then Alice can actually roll back the whole output into the contract output again. So Alice can't take the money here because she's just challenging him. So she's kind of rolling back the contract back to before Bob was trying to claim the money, and also burning Bob's collateral in the process. Okay, so I'll do a brief demo if we can see my screen. Yeah, so the nice thing about having a RISC-V being our compile target is that you can use a lot of high-level languages. So in this case, you'll see a Rust program where we have defined some boilerplate. So there's some assembly setting up everything and calling into this. Calling into this run contract method. So what we're going to do in this case, just as an example of something that's not very complex, but still not easy to do in regular Bitcoin script today, we're going to do some division. So here, we're going to read something from standard input. This is what's it's being put on chain. We're going to just check that it's not a trivial factor. And then we're going to take this number, 901, divided by the input, and check whether the input was a factor of this number. And then we're going to write 1. In the other cases, we're going to write 0 to the output. This means essentially that if you know the factors of 901, then you're able to claim the money in this contract. If not, you shouldn't be able to. Then we'll just... can you see this? Yeah. So this is, we're using a regular Rust compiler for this. So we have the target set to 32-bit bare metal RISC-V CPU. We can build this and get an ELF binary. Then I have this tool called ELF trace, which will actually trace this binary. So what it will do is exactly what I showed. It will take the ELF binary. It will go step by step in the assembly code. It will create a Bitcoin script, write that to file, and in the end, when you have all the scripts, you'll assemble them into a taproot. And in addition, you can give it like an input and an output. And in that case, it will run the full program with that input and then create the computational trace as well. And use that to create the witnesses. Yeah, so I prepared like a simple one here, just for you to see how it looks like, if you can see this though. So this is the add This is like a script for doing the add operation we saw earlier. It takes like something that's in the register, adds a constant to it, and then stores it back into the register. So I won't go through the script. It's pretty crazy. We're doing a lot of cats. So what it's doing here is like since we don't have 32-bit unsigned addition in Bitcoin, this is actually doing like it's doing 32-bit additions using bits here. So it will and actually build the memory representation here, and then do the Merkle proof, and check the Merkle proof against here, and then we'll actually start. Okay, yeah, now it's checking the Merkle root, and then it's going to actually start doing the addition. Yeah, something like, yeah, and so forth. You can fast forward this, and it's verified. Okay, so that was the demo. Maybe not the most exciting contract, but you can write basically any Rust program, right? And that's one of the things that's cool with this. If you have a Rust compiler, then you can tap into like the big ecosystem of Rust programs and libraries that are out there. So what I was able to do last week was to compile the Rust library Winterfell, which is a CK library, using this framework. And that's nice. I have it here. Let's see. Yeah, so the nice thing about it is that as long as the library you're using is not using the standard library, which is not supported at least currently, then you can just import it. You can write your program, take some input, run it on this library, and then output whatever. And then you compile it, and then you run it on elftrace. Elftrace just runs it on a virtual machine and creates the traces. In this case, though, it is fairly slow because it's a very large program. We can start running it here. Let's see. If I have the right command. Yeah, it's this one. I had to skip checking because it's too slow. So this will create like a 3 billion state trace. So it's very slow, but that's fine because we assemble everything into Taproot, and if you put the time locks, you're generous with the time locks on chain, then it's no problem people running this thing. It can take hours, right? Doesn't matter because you have time to respond to if somebody is doing this incorrectly. Yeah, 500,000 different scripts that goes into the Taptree tree in this case. So I'm not gonna go let this finish because it's gonna take a while. But that's the idea, that you can tap into the different libraries that's out there, and then you can run this heavy computation off chain. But the only thing that goes on chain in the optimistic case or in the best case is the input to the program. So in this case, it's the CK proof itself. You need to put on chain. With the example I'm compiling here with like a Fibonacci proof, it's about 2 kilobytes. And you can imagine other maybe snarks or other proof systems are optimized for smaller proofs. So that's what could be best for our case. Yeah, if you want to see more of this and play around with it, here's some links. Also toward the end there, where I showed the actual script that runs in this case. It's a tool I created called Tapsim. So check that out if you want to play around with Bitcoin scripts. It's a Tapscript debugger basically, which I found useful. So any questions? If I got time left. Yes. Yeah. Yes, I commit the input, and so there's different stages here. One is the fraud proof challenge. In that case, it's a trace that's committed to. That's used to actually be able to, like, if you told me this was the trace before this transaction, then you have to be consistent and give me the same or this a subtree. It doesn't have to be. Only the input needs to be. And if you give me some input and I say, oh, the computation with this input is wrong, then give me a trace. And that trace has to be consistent with that input. Yes. Yeah, you need the full trace yourself, or you need a trace, a correct trace. No. So as the spender, you only publish the trace root of your trace. I'm as a verifier, I create my own trace and create my root. And if that's different, then I know that you're lying. Yeah. Okay. You know the full program, you know the input, and from there, since it's deterministic, you can generate it yourself.
Gotcha. That makes sense. Okay, I'll ask one more question, then everyone else can go. But I have more later. But you mentioned like collateral, right? So do you have a system to basically determine like how much collateral should be put up for a particular program, or is that just sort of like hand wave? People will figure out what that value should be.
Hand wave, yeah.
Okay.
Yeah. It's up to the whatever contract you're making, I guess.
Gotcha. Okay.
Yeah, a question back there first.
Yeah, so is the verification happening as part of consensus, as part of this op-CCV?
Yes, so op-CCV is just checking that the input and the output to the transaction, like the key, the taproot key in the input and the taproot key in the output, is consistent with the Merkle roots we're giving it. So it's very simple. It's just check that the key is tweaked with something.
Okay, but so there still needs to be, so if there is fraud that occurs, then there still needs to be a justice transaction. Is that correct?
Well, it's just in the sense, what I'm saying here is like they have some collateral, they have some skin in the game. So if I catch you cheating, then I'll burn that collateral.
Okay, and how many, can you do that in one transaction, or is that going to take multiple transactions?
You need to go through this fraud proof challenge, which is
it similar
logarithmic
to
in the number of state transitions.
Okay.
Do you know like arbitrary, like the OG version, or even like TrueBit? It's similar to that.
Okay, I'm going to have to look that up. But
A question here?
This will be like a game. We can just pass it.
So is it possible that for a given input, the smart contract can be written so that the steps in the smart contract itself are different, so that the traces would be different, but they get the same output?
Well, yeah, so it has to be deterministic. So if I'm not cheating, and even though we get to the same output, if we disagree of how you get there, then I can challenge you. And well, if you're able to prove that your trace is correct, then it doesn't matter. But you need to be careful there. I think if it's not deterministic, then it's not possible to make statements about whether a root is correct or not. So yeah, I don't think you can have non-determinism in there.
So, at the end you showed like the WinterFlow program that was like, much larger. So one question is like, at least with your current implementation on your laptop, like, do you have a metric of like opcodes per second, or like cycles per second, in terms of like how fast the emulation is to generate the trace? And I mean, like the
VM, the trace itself.
Yeah.
I haven't measured that.
Yeah, that'd be just an interesting metric because, like, for example, people like RISC-V, they have like a kilohertz, megahertz metric that they look at, but that's like with the optimized GPU thing,
this is based on the RISC-V VM.
Yeah. I mean, the interesting thing about this that like all of this looks like Starks without privacy, basically. Like you have a trace, you make a Merkle over the trace and so forth, but Starks add privacy, which is the heavy machinery, you can say.
So it's basically what we do. We do use the RISC-V library, which they have a VM for making CK proofs over the computational trace. So we just like cut that short. We just run run it with the RISC-V VM, the CK VM, and then before we start creating the CK proofs over the trace, we just take the trace and Merkleize it. So that's what we do. So it should be faster than that, at least.
Sure, yeah, you don't need that.
We don't need the CK part.
Probably a stupid question, but can you talk a little bit more about burning the collateral? And like, is that like sending the Bitcoin to an unspendable output or something, or just talk about the mechanics and kind of?
What I do is just like put it to
seizing?
fees. Put it to fees.
Yeah.
I think you should just, well, if you had amount introspection, you could probably do like very interesting things with the collateral. It makes it maybe part of the, maybe Alice gets part of it. If you catch Bob cheating, has an incentive there. It's just, yeah, I think it's up to whoever's writing the contract, and with tools like amount introspection, you can do whatever you want.
Got it. Cool, thank you.
Well, yeah.
All right,
Okay,
I have my last question. What was the like cumulative size of the ad script that you had there? So you had the initial script, that was, or no, it was division basically. So like if you sum all of the tap leafs up, the ones that weren't published on chain, what's the size of that?
Oh, yeah.
Because I saw you're saying that you did bit composition for the addition, which is obviously more expensive than doing the opcodes. Just curious about like what the raw size of the sum of all the leaves is.
Yeah, so in this case, I think the addition script is here. It's about 2 kilobytes. So remember, this is very naive. This is just me doing like bit addition. So this is one of the larger opcodes because you actually have to do this 32-bit arithmetics. I tried to do the multiplication as well, but that one became larger than the 10 kilobyte limit on the script. So I just like changed to a compiler target that doesn't have multiplication, so I don't have to deal with it.
But I guess you could do like a continuation like that too, right? In terms of like, I guess like checkpoint the state and then resume it in another script to get around that 10K limit, or?
Yeah, maybe like, you can do it like on the compiler stage.
Yeah, that's effectively what Zero does as well in order to do recursive proofs in their system. So maybe there's something you could take from there as well.
Or maybe you can just do a 8-bit target or something.
yeah. Small numbers.
It doesn't really matter how long the trace is because you're going to Merkleize it, so it's going to be a small one-chain anyway. Back there. Last one, I guess.
So this is kind of an open-ended question that I like to ask. So if you were a dictator of Bitcoin for a day.
Just for a day?
Just for a day. That's all you really need, actually. What kind of, like, how would you implement this in a more efficient manner?
I guess to be a nice guy, I wouldn't change Bitcoin in a day. I would propose something and then let the community decide that. No, I think,
humble.
I think I would like just a bunch of introspection opcodes and EC operations, so I could like check tweaks and check build tap trees and whatever I want to do in script.
Okay, so more introspection.
More introspection, yeah. And then better arithmetic, like you're saying, so do decomposition. Oh yeah. So the thing here is that this is a 32-bit unsigned target, so I need to be able to do like 32-bit unsigned adds, but Bitcoin script only has 31-bit. So I add 1 bit too little, so I had to re-implement everything in order to make it work. So better arithmetics would be very useful to just cut down the size of the scripts. All right, thanks.